Section: Introduction. In this section, we discuss the development of Vision Language Models, VLMs, that enhance large language models, LLMs, by enabling them to process visual information. This capability allows VLMs to handle a wider variety of tasks, leading to increased interest in their application for intelligent agents, autonomous driving, and embodied AI. We have seen significant advancements in the architecture and training of VLMs, particularly through post-training methods on pre-trained LLMs, with the LLAVA family serving as key examples. We categorize current VLMs into three types based on transparency. 1. Closed-source commercial models. 2. Frontier models with publicly available weights. And 3. Fully open-source models. Notably, some frontier models have demonstrated performance comparable to closed-source models while allowing for better customization. However, the technical details provided by these models often fall short for reproduction purposes. In contrast, fully open-source models tend to share extensive technical information, which aids in the development of customized VLMs but still often lag behind frontier models in performance. To address the question of how to create more competitive open-source frontier VLMs, we focus on data strategy. We believe that, given the same pre-trained LLM backbone, data quality is crucial for building high-performing models. We implement a centralized approach to our post-training data, recognizing that constraints like computing resources can limit fully open-source models in exploring diverse datasets. Our guiding principle is diversity first, then quality, which we apply rigorously. Our contributions include 1. A strategy for collecting a large and diverse data pool from over 180 sources. 2. A filtering strategy to eliminate low-quality samples. 3. A selection strategy for high-quality subsets. And 4. Various data augmentation techniques to enhance our dataset. These strategies have led to significant model improvements. In addition to data strategy, we also consider model architecture. While many designs have been explored in open-source models, the simple MLP connector remains the most common choice for linking the vision encoder and LLM. Although architecture is not the main factor affecting performance differences anymore, there is still potential for improvement. We adopt a vision-centric design that incorporates dynamic tiling and a mixture of vision encoders, MOVE, allowing us to process high-resolution inputs effectively. Our configuration, which combines SIG-LIP with ConvNeXt, shows notable performance gains, especially in tasks like OCR and document visual question answering. Regarding the training recipe, we recognize that different configurations can significantly impact model performance, even with the same dataset. We employ a three-stage training strategy to optimize our training data usage. The first stage aligns the language and image modalities, the second stage trains the full model with a diverse dataset, and the final stage fine-tunes the model with a high-quality visual instruction dataset. By incorporating all available visual instruction data in the second stage, we achieve substantial improvements over traditional two-stage training methods. We also identify and address limitations in existing open-source frameworks related to data packing by introducing a balanced data packing approach. Section Summary. In this section, we discuss the development of Vision Language Models, VLMs, that enhance large language models, LLMs, with visual perception, emphasizing the importance of a robust data strategy and model architecture for improving performance. We propose a centralized data collection approach, a three-stage training strategy, and innovative architectural designs to create more competitive open-source VLMs, addressing current limitations in the field. Section: Summary. In this section, we present our comprehensive investigation into data strategy, model architecture, and training methods, which led to the development of a group of models called Eagle-2. Our goal is to share our exploration process, allowing readers to learn from our experiences rather than just providing them with results. The Eagle-2 family includes models with different sizes, such as those with 1 billion, 2 billion, and 9 billion parameters. Notably, The Eagle 2 model with 9 billion parameters can compete with or exceed the performance of leading open-source and proprietary models on various multimodal benchmarks. We begin with a baseline using the Cambrian dataset and Java's two-stage training approach. We filtered out low-quality data from the Cambrian 7M dataset, resulting in a refined set of 5.2 million samples. Our model connects the vision encoder to the language model using a multi-layer perceptron and employs image tiling for varying resolutions. We enhance Eagle 2 by focusing on three main areas: data strategy, training methods, and model design, which together help us achieve top-tier performance. Data strategy is crucial for defining the capabilities of a visual language model, VLM. While many commercial models keep their data strategies secret, we explored ways to create a diverse and high-quality dataset. Our data strategy involves two main components: collecting new data and optimizing existing data. We emphasize diversity in our data collection, using both passive gathering, monitoring new datasets, and proactive searching to address gaps in our data pool. We summarize our diverse data sources, which are generally publicly available, and ensure careful inspection to avoid issues like test data leakage. To quantify diversity, we developed a similarity score metric that measures how relevant new data sources are to our existing pool. This score helps us identify and remove duplicate or low similarity samples. Our final model includes 21.6 million samples in the first stage and 4.6 million in the second stage, with over 20% being text-only data. We also focus on filtering out low-quality samples, which often include mismatched question-answer pairs, irrelevant image question pairs, repeated texts, and formatting issues. By applying rule-based filtering, we can effectively remove these low-quality cases. Selecting optimal subsets of data is essential for high-quality training. We limit the number of samples from each source based on diversity and distribution, using k-means clustering to ensure balanced representation across different types of data. Data augmentation is another key aspect, where we extract additional information from images using third-party models to generate detailed descriptions. We also format our data carefully, ensuring that similar tasks have consistent formats while different tasks are clearly distinct. This includes removing unnecessary elements and adding specific instructions to improve model performance. Section Summary. In this section, we detail our development of the Eagle 2 family of VLMs, emphasizing our iterative approach to data strategy, model architecture, and training recipes, which collectively enhance performance across various multimodal benchmarks. We also outline our comprehensive data collection and filtering methods, ensuring high-quality, diverse datasets that significantly improve model capabilities while maintaining rigorous standards for data integrity. Section: Training Recipe. In this section, we outline our training strategy, which allows us to create a high-quality and diverse dataset. However, we recognize that different training methods applied to the same data can significantly affect the results. Our approach is based on several key points. First, we emphasize the importance of a post-pre-training stage. We start with Java's two-stage training, where we first train an MLP connector and then the full model using SFT data. While this method is efficient, it struggles with rapid updates to SFT data, making it difficult to track the effects of new data and reducing experimental efficiency. For example, we see improvements when we expand the Cambrian 1 SFT data, but there is still a gap between our model and the best-performing models. To address the limitations of the two-stage strategy, we introduce an additional pre-training stage, which we call STAGE 1.5. This stage pre-trains the model on a larger dataset, reducing reliance on SFT data in later training. Next, we discuss the importance of balance-aware data packing. By concatenating shorter samples, we can speed up training and reduce padding. Our experiments show that this method can accelerate training by 2 to 3 times. We arrange multiple short samples into longer ones without exceeding the maximum length. While existing methods often lead to uneven length distributions, we develop a balance-aware greedy knapsack algorithm that ensures a more uniform distribution of lengths in each pack, helping to balance the loss weights between long and short samples. We also utilize a mixture of vision encoders, specifically SIG-LIP and Convenext XX Large, to handle high-resolution images. We tile images to ensure consistent output sizes from both encoders, allowing us to concatenate features and align them with our language model. In our exploration of scaling Stage 2 training data, we find that overall performance improves with more data, particularly with the addition of 2 million VQA samples focused on charts, tables, and OCR. However, we face challenges as performance fluctuates across benchmarks, especially in difficult areas. This leads us to implement STAGE 1.5 to maximize data utilization and strengthen the model's foundation. Our findings show that the STAGE 1.5 checkpoint is competitive, and further training in Stage 2 improves performance by an average of 3.9%. We also experiment with naive data selection, which unfortunately reduces performance due to the exclusion of valuable samples. After filtering low-quality data and formatting our training set, we see significant improvements across several benchmarks. By employing a more advanced data selection strategy, we further reduce our dataset while enhancing quality and achieving better average scores. Additionally, our data augmentation strategy introduces more automatically generated training data, leading to notable performance gains. We apply effective data strategies from Stage 2 to update STAGE 1.5, resulting in clear improvements in various benchmarks. Overall, the introduction of a mixture of vision encoders has enhanced our model's performance across most benchmarks, particularly in areas related to documents, charts, and OCR. Section Summary. In this section, we outline our training strategy, which includes a necessary post-pre-training stage, Stage 1.5, to enhance model performance by utilizing a diverse dataset and implementing a balance-aware data packing algorithm to optimize training efficiency. We also discuss the benefits of using a mixture of vision encoders and advanced data selection techniques, which collectively lead to significant improvements across various benchmarks. Section: Comparison with SOTA models. In this section, we compare our model, Eagle 2 to 9B, with various state-of-the-art models across 14 different benchmarks. Our model, which builds on Qwen 2.5-7B, outperforms Intern VL2 to 8B and Mini CPM v2.6 in all benchmarks. It also leads Qwen 2 VL7B in 9 out of the 14 benchmarks and performs better on OpenCompass. Despite being smaller, Eagle 2 to 9B competes well against larger models like Intern VL2 to 26B, LLAVAON EVISION 72B, and LLAMA 3.2 to 90B Vision. We significantly outperform GPT-4V, except in MMVet and MMMU, and we surpass GPT-4o on ChartQA, OCR Bench, and MathVista, while closely matching its performance on DOCVQA, MMStar, AI2D, and OpenCompass. Regarding related work, we note that vision language models, VLMs, have greatly impacted natural language processing and the AI field. The progress in large language models, LLMs, has enhanced visual understanding by combining visual features with LLMs, leading to the development of VLMs. Publicly available VLMs are achieving impressive results, often matching or exceeding advanced commercial models like GPT-4V, 4o, and GEMINI 1.5. The release of fully open-source VLMs, along with their training data and code, has further propelled research in this area. Our approach focuses on a vision-centric VLM design that prioritizes a strong visual foundation and high-definition input. This aligns with several related areas, including vision foundations for VLMs, various vision encoder designs, and high-definition input strategies. To our knowledge, we are the first to investigate the tiled mixture of vision encoder design, which combines the advantages of both approaches and adds flexibility for integrating advanced vision models. Data strategy plays a vital role in training VLMs, involving dataset construction, balance, filtering, and training methods. Early models like LLAVA 150K utilized instructed tuning with GPT-4, which was later enhanced by incorporating academic training data into the fine-tuning process. Researchers have expanded data types to include videos, multi-image inputs, and multilingual data, but simply increasing dataset size can hurt model performance due to quality variations. Models like InstructBlip and Cambrian-1 have tackled this by optimizing data ratios and balancing techniques, while others like Llama 3 and Molmo have focused on improving data quality by removing duplicates and using human-annotated images. Training strategies have also progressed, with LLAVA introducing a two-stage training process that has become a standard, and subsequent models adding intermediate stages. While VLM surveys discuss various training recipes and data strategies, they often lack qualitative analysis and do not provide a clear path for training cutting-edge VLMs.